Hello students, welcome back. Let's go to section 3 and let's try to complete it this time. Our target is this kind of equation. Homogeneous linear ODEs with variable coefficients where each coefficient function is a linear polynomial of t. We went through one example like this before and we have a couple more and let's try to complete it. Now what is our main tool? This formula here, or equivalently speaking, the derivative of the output function is the Laplace transform of negative t times y of t. Or okay, there you go. So the derivative corresponds to this multiplication, or equivalently, the derivative corresponds to this multiplication and negative. That's our main tool. And let's go to the second problem. Okay, very similar to the previous problem, but if you do it right, there's going to be a bit of a surprise in the end. The first step is always breaking up. Okay, why? Look at this formula here. When it's t times something, not parenthesis open something something times y. When it's t times something, that's why I have to break these up. And then let's take the Laplace transform. Excuse me, let me copy and paste this thing. And then let's take the Laplace transform. Okay, all right. And please recall we have t here, we have another t here, and they're going to be requiring the output derivative formula. Otherwise, okay. The Laplace transform of 0 is of course 0, no problem there. The Laplace transform of y is capital Y, again no problem there. And then how about this y prime? We can use the input derivative formula. I hope everybody remembers. And, well, how about these? Well, looks like it needs some work. Remove this t. That's the derivative. And I need this minus. Remove this t. That's derivative. And then I need this sign change there. See? This minus t, excuse me, that's t, gave me this minus sign and the derivative. This t here gave me this sign change and the derivative. Actually, I was a bit premature in these computations here. So let me bring these back. Okay, all right. Okay, now let's take Laplace transform of 0. That's 0. Laplace transform of y prime is that. And then the Laplace transform of y prime. Okay. All right. It goes over here. Sy minus y naught. And then this one, s squared y minus y naught s minus y1. Okay, those were input derivative formulae. I hope everybody still remembers everything. And let's take the derivatives. Let's see, take the derivative. This is 2sy plus s squared y prime. And then this will be gone. I completed all the derivative computations, so I don't need this prime. And there you go. How about this one? Y plus s y prime, and I don't need this, and all looks good. Now the resulting equation here is what do you call the first order linear equation, first order linear ODE. So you can solve it using the method of integrating factor. So how do you do it? Well, I will save some time, so let me open up this and then let's go. But there's a bit of a digression to make, actually. I realized I forgot to talk about this Laguerre equation, actually. This thing is called Laguerre equation of order 2. This number is 2. In general, we have order n here. And bigger the number here, bigger the integer here, the more complicated this equation. In this case, I'm keeping as 2, and all these computation I just use 2. But then again, as a matter of fact, if I use some n here, arbitrary n here, what makes a difference here? So far, the difference is actually minimal. The difference is minimal. So that's what I'm going to do. In this notebook, that's what I did. I just kept n as arbitrary and plugged in n equals to 2 toward the end so that you can use the same technique for all Laguerre equation. That's what I did here. Kept all the n's and then take those like terms together and then put those into the standard form where we have y prime plus p of s y equals to f of s form, like this. It turned out that f of s here in this case is 0. Let's see, we have minus y0 and minus plus, and then we have minus. So yeah, these two cancel out and no constant. So we have 0 over there. So in this particular case, f of s here, this one is 0. So you're going to get something really simple. Okay. So far so good. We are getting something simple here. I always like 0. Okay, alright. And let's solve it using the method of integrating factor. What is the integrating factor? Does everybody recall? E to the q power. This is integral of the antiderivative of. And what is p of s? It's this one over here. So you must calculate this integral first, and then take e to that expression, and that's the integrating factor. This integral, it looks pretty bad, but don't be intimidated. I'm not going to ask you to do this by paper and pencil method. You can always use computer algebra system to take it apart, decompose by partial fraction, and then you can use logarithms. Well, would you like to try? Maybe you can stop this playback and try that on your own. The mathematical code is apart, and then I can always copy and paste. And here we go. Well, here's the answer. There goes a partial fraction here, and we end up with this. There are too many fractions and exponentials, so let me increase the font so that I can read things better. Okay, so this fraction can be decomposed by partial fraction like this, and then logarithm minus logarithm, put those together and we have log of this fraction. Putting those into single logarithm makes a lot of sense because we are going to take exponential. An exponential and log will cancel each other out, and we are going to get this fraction there. That's the integrating factor. Make sense? Now multiply this integrating factor to the original, excuse me, not the original, this equation here. And then left-hand side can be always consolidated into a single derivative, mu times y. And the right-hand side, as a matter of fact, you're supposed to get f of s times mu of s. But then again, f of s in this particular case is 0. So 0 always makes our life easier. So multiplying by 0, I don't have anything there, luckily. So taking the antiderivative, I simply get c. Again, great. And divide away by this integrating factor. Here we go, I have capital Y. So all I have to do now is to get small y by taking the Laplace inversion, and that's about it. Now, given a function like this, how to take the Laplace inversion? Does everybody recall? You have to break it apart, right? Break it apart, decompose by partial fraction, and then each fraction will have Laplace inversion, and you can get those from the Laplace table. But then again, how do you break this one apart? Oh, that's going to be a problem because nth power, that nth power can be arbitrarily large. Oh, okay, all right. At this moment, I give up. I cannot keep this arbitrary order anymore, and let's keep it as simple, n equals to 2 right here. Up to here, having arbitrary order of Lagrange equation versus Lagrange equation order 2 made little or no difference. Very little difference, but from here it'll make big difference. So, okay, put n equals to 2 and decompose by partial fraction. Now that's what we get. S minus 1's total quantity squared over s cubed. Take the complete square, and then this one didn't even require a computer algebra system. Most of the time, decomposition by partial fraction requires some computer algebra system because it can be really horrendous, but not in this case. It was easy. So, okay, let's take the Laplace inversion. We have the answer. So, is everybody happy with this answer? And here is the checking process. Is everybody happy? Or is there anybody who is feeling a little bit uneasy? I said there's a bit of surprise in the end. Do you see the surprise? Okay, let me show you the previous problem, the answer to the previous problem. Here's the final form. In the end, after consolidating these two, we have different character here. So what did we end up with? We have a linear combination of two linearly independent solutions, e to the t power and t plus 1. We have two solutions, and then we have two coefficients b and c. So we have linear combination of two linearly independent solutions. So this is the general solution. All right? Now let's go back to this. We have only one arbitrary constant c. So this is not a general solution. It can't be. I found only one solution. What's the second solution here so that I can take linear combination? That's the surprise here. The answer, we can't find it. It's impossible. Because the second solution, it'll turn out the second solution does not have valid Laplace transform. It's not one of those functions of exponential type. So it doesn't have, excuse me, I take it back. It's not because of it, it's not the exponential type. It has more to do with possible initial condition. Anyway, never mind, I don't want to get too deep there. Anyway, the second solution does not have valid Laplace transform. So the Laplace transform method did not find it. It found only one solution. Now, how do you find the second solution if you need a general solution? That's something we're going to do in section 4. At this moment, we'll have to just give up with just one solution. We'll have to just contend with the first solution here. Enough time for the next problem here. Okay, all right, let's go. But this time, let me move on rather quickly. This problem, and everything is already broken up, so I don't need any breaking up. So let's go ahead and take the Laplace transform directly, and then apply the... Okay, all right. Let me take one more step here. Remove this t derivative, but with this negative sign, output derivative rule. So we have this t, so remove this t. And then we need derivative, but then again, we need the sign change because of this negative there. Okay, output derivative rules. And then you can plug all those inside input derivative rules there. Take the like terms together. And then simplify. It turned out that capital Y term disappear. Let's see, we have negative 2sy and then plus 2sy, they disappear. And all I get is capital Y prime equals to that. Oh, that's easy. So capital Y is nothing more than the antiderivative of this expression. And what is the antiderivative of this? Negative 3y0. And what is the antiderivative of 1 over s squared plus 1? It's arctangent. Okay, we have this. All I have to do now is to take the Laplace inversion. Great. What is great about this? What is the Laplace inversion of the arctangent function? Uh-oh, we have a problem. How do we handle this? Any idea? I mean, we found capital Y, yeah. And the final step would have been taking the Laplace inversion, but I can't do it. Something is not right. How do you make it right? Well, if you want to think a little bit more, then stop this playback and think about it. Otherwise, here's the answer. Instead of going to y, it's better to take the Laplace inversion here, because look at this. This is a rational function. Some constant over s squared plus 1, and look up your Laplace table. What's the Laplace inversion of this? You're going to get what function? Page 123, what is it? You're going to get sine function. Here we go. Take the Laplace inversion right here. So L of ty is minus y prime. So if we take the Laplace inversion here, instead of getting y, you're going to get t times y. That's the trick. So here we go. L of ty is negative y prime, and dropping this negative, we have this rational expression. And let's take the Laplace inversion right now, then ty, because that kills this, equal to the Laplace inversion of this rational, which is a sine function. And ty is equal to sine, divide by t, then I'm going to get y equals to k times sine over t. That's how we get the solution. As in part B, we have only one solution, because the second solution will not have the valid Laplace transform. So we can find only one solution. How do you find the second solution? That's going to be a topic of section 4. For now, let us be content with just one solution. That's all the Laplace transform method found out.